TWiM listeners, do you have science you want to share? Microworld.org is the best place to post your microbiology-related news articles, pictures, videos, papers, and more. Sign up for a free account at microworld.org/join and start reaching thousands of microbiology enthusiasts just like yourself.
This Week in Microbiology is brought to you by the American Society for Microbiology at microbeworld.org/TWiM. This Week in Microbiology, episode number 87, recorded on September 11th, 2014. Hi, everybody. I'm Vincent Racaniello, and you're listening to TWiM, the podcast that explores unseen life on Earth. Joining me today from Small Things Considered, Elio Schaechter.
Hi, how you doing?
I'm well. I hear you got some rain out there. Is that true?
No, we did not. Anyhow, we wouldn't even know how to spell it.
I was watching a weather report, and they said Southern California was going to get inches of rain.
They did in the mountains and the desert of all places, but San Diego didn't.
Oh, I'm sorry.
And it's a disaster. I mean, really, we have this deep, deep drought, and who knows what's going to happen.
Well, someday you'll talk about it in retrospect.
I hope so.
Also joining us today from the Medical University of South Carolina, Michael Schmidt.
Hello, everyone.
How are you, Michael?
A little bit wore out this week. I had a busy weekend and then a busy first 2 days of the week. I attended ICAAC, the Inter-Science Conference on Antimicrobial Agents and Chemotherapy that was held in Washington, D.C.
Wow, you're getting good at saying that. I remember when we all used to mess it up.
You only have to say it about 50 times and then it becomes normal.
Yeah, inter-science. That's the word that's a little strange. Inter-science. I mean, there's only one science, right? Science is science.
Inter-sciences.
There's different sciences, like microbiology and biochemistry and physics.
Yeah, so, I think today if we were rewriting the first words of ICAAC, it would probably be interdisciplinary.
Yeah, that's a better one.
But I don't think that word existed 54 years ago when ICAAC started.
Yeah, and I don't want to change it. All right. Well, we're going to hear from you a bit later, but first, Elio has a couple of things to tell us.
Well, the first one has nothing to do with the way we usually discuss science. Just a little thing that happened is I was sitting, listening to somebody give a talk on the human microbiome, and he said that it's estimated that an average human being carries inside on him, her, something like 10 to the power 14th bacteria. Okay? 10 to the 14th is a huge number, and it's due to the fact that bacteria are small, and we do have lots of them. So I was doodling and thinking what to do with this number, and then it occurred to me to multiply that number by the number of estimated people on Earth, which is something over 6 times 10 to the 9th. So 6 times 10 to the 9th times 10 to the 14th is 6 times 10 to the 23rd. Now, you will recognize that number as being Avogadro's number. Okay? So that's the number of atoms in 1 mole of atoms. That is, if you take the atomic weight of atoms and translate that into grams, you have Avogadro's number of atoms. And that's a universal truth. So anyhow, so it occurred to me that if you wanted to find out what is the size of Avogadro's number, which people did over 100 years ago, all you have to do is to count the total number of bacteria on all the human beings on Earth.
That's right.
That comes out to be Avogadro's number. Anyhow, I looked up Avogadro just for the hell of it because it occurred to me. I mean, who knows who Avogadro was? And, you know, it's something about eponyms. Not all eponyms. Eponyms are things which are something named after somebody. Like Petri dish is an eponym for Petri. So it occurred to me that not everybody who gets something named after them, even if it's very important, really makes it out. And a good example is America. America is named after Amerigo Vespucci. Now, I'm going to double dare you. How many things can you say about Amerigo Vespucci? Nothing,
I
right?
didn't even know that fact.
Okay.
Is he Italian at least?
He was an Italian explorer.
Okay.
That's it.
That's all I know.
Whereas Columbus, who everybody knows something about, we don't call it Colombia, we call it America. So Avogadro is the same thing. Having your name attached to something doesn't mean you're gonna make it. So it turns out that Avogadro was kind of interesting. He was a early 19th century Italian physicist in Turin, and he was a nobleman. Okay, but he was a revolutionary because at that time the king of Piedmont, there was no Italy yet. The king was not a very liberal guy, and so there were revolutionaries, and good old Avogadro, although he was from the aristocracy, was against that, and he lost his job as professor for 10 years. But then the king relented, and they wrote the constitution, and he got his job back. Now, the funny part is that it wasn't called Avogadro's number for 100 years. Until 1908, when a Frenchman named Perrin thought, gee, we should give this number, we should call it after somebody. And since Avogadro had figured it out, no doubt that he was sort of the first guy to figure this out, it became known as Avogadro's number. But nice. Now it got repaid to Perrin because Perrin figured out the size of Avogadro's number.
Right.
And for that, he got the Nobel Prize.
So Avogadro just said there's a fixed number of molecules,
that's right?
Or
that's
atoms,
right.
And yeah, so
in 1 mole.
Yeah. So of course there's Mole Day, which is October 23rd, right? It starts at 6:02 a.m., 6:02, 10:20, and it ends at 6:02 p.m. And at school, they always do that with the kids in high school and middle school. Today's Mole Day to explain it, to make it more.
Very good.
So 10 to the 23 bacteria in us.
No, on the planet.
On the planet, sorry, 10 to the 14th.
So
I got to say, it does not approach the number of viruses on the planet, which is 10 to the 30th.
Or 31st.
Or 31st. Who's going to quibble with one more, right?
An order of magnitude.
Although at that level, it's a lot, right?
It is.
Going from 10 to the 30 to 31. That's enough. If you put them head to tail, that would stretch 200 million light years.
Oh, my God.
And these are invisible things.
And these are nano-sized
Yeah, that's
things.
the thing that's amazing, that you can't see them yet. There's so many that they would stretch that far. It's amazing. And at one point, we had no clue that we had all these things on the planet or in us. Isn't that amazing?
Now, in your calculation,
That's
do you add computer viruses to this too?
No.
They're not that many.
Yeah, they're probably not anywhere near as many. That's
right.
Absolutely. Well, that's great.
Yeah.
Avocado's number, I like to call that.
Not avocado. Come on,
I know.
avocado. Oh, boy.
You've been hanging out at Whole Foods too much, Vincent.
I do like avocados, don't you?
Yes.
Anyhow. So, would you like me to go first?
Yes, please, Elio. And I'm going to let you introduce it, because this paper that we read for your selection today is very difficult.
It's in fact so difficult that it is not reasonable to discuss it in any detail, and I won't do that. But let me just tell you the title. Gives you the idea. It's published, first of all, it's published in a journal that most listeners here don't usually read. It's called Geobiology. It's a wonderful journal, really, because it deals with things that we normally don't deal with. And in this case, we're going to deal with something called biomarkers. And biomarkers are molecules which are left behind when animals, plants, bacteria, archaea died, and they become a marker for their past existence. And a lot of things. I'll give you a little talk about biomarkers, but let me just round this up by giving you the title of the paper, which is Fossilization and Degradation of Archaeal Intact Polar Tetraether Lipids in Deeply Buried Marine Sediments of the Peru margin. And the authors are Sabine Lenger, Ellen Hopman, Jan Sinninghedamste, and Stefan Schouten at the Marine Organic Biochemistry Department of the Royal Netherlands Institute for Sea Research in the Netherlands. These people have been working on this kind of subject for a long time. So we're talking here about Archaeal intact polar tetraether lipids in deeply buried marine sediments. Okay, so let me start out with the general concept of what biomarkers are, what good they are, and give you a few examples, and then say just a couple of things about this paper. So clearly, without even thinking about it, it's clear that the best biomarker you could probably wish for is DNA. RNA, by the way, is not likely to be much of a biomarker because it's very labile. It's destroyed very easily. DNA, by virtue of being double-stranded, is much tougher, and it sticks around some. However, it doesn't stick around forever, and just how old a useful piece of DNA is not known. It's not found in actual fossils. It's found in fossilized material, let's call it. And it's not found in real rocks. And the best I can tell you is that, in amber, one finds living or not living, extant biological material. There's been a lot of work done with material extracted from amber. But when all is said and done, there seems to be about a limit of about 1 million years for how old the useful DNA is that you can get out of material. It's very argumentative, and I won't defend that. And please don't hit me over the head, because it takes experts to really figure this out, and the experts don't agree with each other. So
you're saying that the oldest known DNA is about 1 million years old? The
oldest useful. Yeah. DNA breaks down, and if it breaks down sufficiently, you got a bunch of oligonucleotides or something.
Mm-hmm. Yeah.
So it's around, I don't know, it's some number. Okay, it's not. There's material. I'll give you a good example, actually, of material which is useful in the permafrost, old permafrost. In other words, ice. You can find stuff which is not fossilized, just frozen. Well, that's very good. And there you can find in a lot of plants in the permafrost material which is 400,000 years old, DNA which is 400,000 years old. And you can use it enough to tell what the plants were. And you can compare it you have an independent measure, because you can look at the pollen, and the pollen is well preserved, and you can date it. And so you can compare the values from the DNA with something else, which is very useful. And there this is terrific. This is very good stuff. But it's a specialized environment, so you can't do this for dinosaurs, right? People think they can. Some people think they can, but it's not likely to be a very useful sort of a thing. So DNA is doesn't buy you an insight into what happened 2 billion years ago, right? I mean, you can quibble about the number, but it's not a very old age sample that you're going to deal with, okay? So what are you going to look at? Well, all kinds of other biological material, and even inorganic material. There are trace metals that are associated with, for instance, melanin. And so if you want to see whether a dinosaur had melanin in his skin, you may want to look at some trace metals and derive something out of it. But there are many other compounds, and the list is quite large, but there are some main ones, and I'd like to sort of tell you a little bit about them. The main ones is a series of compounds called the Hapanoids, Hopanoids, Hapanoids. And they're lipids. They are pentacyclic. In other words, they have 5 rings, and they look a lot like a steroid. Now, if our dear readers can picture a steroid in their head, it's something made up of usually 4 rings, and with some side chains. This is 5 rings, and they are Hapanoids. By the way, where does the name come from? They come from a resin-making plant called Hopea, which is named after an English botanist, John Hope.
They're having to do with beer?
Hops? The hops?
Oh, boy. No. This is Hope. No. Sorry about that. but anyhow, there is an eponym for you. So hapanoids are called after eventually. Anyhow, they are membrane components. They are found mainly in aerobes such as cyanobacteria, and they go back in rocks. Get this, 2.7 billion years ago. Okay, so if you extract rocks with organic solvents, you get hapanoids. Not only do you get hapanoids, it is said that they are the most abundant organic set of compounds on Earth. Can you believe that? And most people never heard of them, right?
Yeah, I noticed the number. They have a huge number for the quantity here in this paper.
That's right. Well, this is...
And remember, oxygen emerged on this planet about 3.5 billion years ago. So they had a billion years to get the hapanoids right.
No. Wait. No, not quite. You're off by a billion years, I think. The numbers I saw are that oxygen in abundance, at least, came about 2.5 billion years ago, and these guys are 2.7 billion years ago. So you're right in one sense.
Yeah.
There was some oxygen.
There was some oxygen, but it didn't get up to high enough partial pressure until...
So that's something like that. Yeah. Anyhow, so hapanoids, what do they do? Well, they seem to be... Just like steroids play a role in the membranes of eukaryotes. Steroids, by the way, are found in just a handful of prokaryotes of bacteria, but they're not common at all. But steroids are very common in every other kind of cell. That's why cholesterol is essential, even though it's bad for you in large amounts. That you can't live without cholesterol in the membranes. And what these compounds do is to strengthen the membrane in some fashion. I won't go into that because for one good reason, I don't know why this is. I can't give you a good reason, but they do strengthen things. And they play some interesting roles in odd situations. The bacteria called Streptomyces, which look a lot like fungi, like molds, because they have aerial components. That is, if you look at them on a moldy fruit or on a petri dish, they have things that stick up in the air. Well, sticking up in the air means they have to go through a water-air interface, which is complicated. And the hapanoids apparently play a very important role in the membranes of Streptomyces and these actinomycetes that make this. Now, there are all kinds of hapanoids. They're found in rocks. They're found in petroleum. By the way, petroleum is sort of an odd case. It's of course organic compounds. You can say all of petroleum is a biomarker if you believe in the biogenic origin of petroleum. Another controversial subject that I'm not about to get into. Okay. Anyhow, so hapanoids, which are found in extant bacteria, they're not that common, but quite a few bacteria make them, especially cyanobacteria and Streptomyces. So they are extremely interesting compounds, and they serve as biomarkers. So we already alluded to that, finding them at a time when finding them as part of cyanobacteria, and you can kind of tell which ones they are. So 2.7 billion year old hapanoids tell you there was not only cyanobacteria, but there was some oxygen. So this is a very useful biomarker, right? You like that?
It's good. Yeah.
Yeah.
Okay. All right. So let me give you another couple of examples, or at least one more example. It's polyamines. Polyamines are hydrocarbons with nitrogen. And they are found essentially in all living things, where they play a role in regulation. They are important in a variety of ways. They also combine with silica. Why do I bring up silica? Because they are found in fossil diatoms. Now, why do I bring up diatoms? Well, diatoms are one of my favorite kind of organisms. They are beautiful, they are interesting, they are varied, and they're ancient. Now, you find polyamines in a lot of things, but finding them in very ancient diatoms is really quite interesting. I have to now. How come you find them? Well, diatoms are made up of silica shells. In other words, glass. Okay, they're surrounded by shells of glass, and shells of glass last forever. In fact, the shells of fossil diatoms are what makes mountains. They make rocks, silicious rocks.
The White Cliffs of Dover.
No, those are calcium carbonate, actually.
Yeah, that's true. They're not crystals.
Right, but you find silica in huge numbers, and they are the shells of diatoms. I want to quote something from a friend of ours and a friend of this podcast called Mark Martin, who teaches at Puget Sound University. And he says, this is because we wrote something about the polyamines of diatoms in Small Things Considered, the blog. So he writes, this puts me in mind of Shakespeare's Julius Caesar. The evil that men do lives after them. The good is often interred with their bones. So microbial bones are polyamines.
Right.
I think that was pretty good. So anyhow, these are, notice that they're terrifically useful because these again go back 100 million years, and you can tell the polyamines are tough stuff because they look like modern polyamines. By the way, 100 million years ago is the low Cretaceous. Since we're talking geology here, let me use the name of a geologic period. And it was a time with high CO2 and high silica in the water. So that's why they made a lot of diatoms, and they went ahead and did a good job of maintaining themselves. Okay, so these are two classes of biomarkers. We've seen the hapanoids and the polyamines. Now let me come to the ones that are the subject of this paper. And they are really particularly interesting. They are the lipids that you find in archaea. Now, let me back up a little bit. Bacteria and essentially the rest of living things in their membranes have phospholipids, which are usually 16, 18 carbon long. That is in the phospholipid. Phospholipids are phosphate, glycerol, and fatty acids. The fatty acids are just dangling there, and they are about 16, 18 carbon long. Now, as probably most listeners know, they make bilayers. That is, two sheets of phospholipids come together, and they face each other by the hydrocarbon end, by the fatty acid end. Tell you what you can do. You know, this is not visual, but we can do it anyhow. Let's take the two fingers of one hand, the index finger and the middle finger, and the two fingers of the other hand, and join them together, but at 180 degrees. Okay? Can you do that? Are you doing that while I'm telling you?
Yeah. I'm doing that while you're telling me.
So now you have a lipid bilayer, okay? You have the equivalent of a lipid bilayer. In other words, it's called a bilayer because it's made up of two layers. Enter the archaea, and by gosh, they do something very different. Instead of having a bilayer, they have a monolayer. So imagine that your two sets of fingers are joined at the tip. Okay? Now you have a monolayer that's twice the length of a typical bilayer. Okay? So these are different kinds of lipids, obviously, and they are sort of a hallmark of the world of archaea. Now, these, of course, are tough molecules because they are held together by covalent bonds. So these isoprenoid chains, they're called isoprenoids because they're polyisoprenoids, because they're made up of isoprene units. And they make a membrane just like a lipid bilayer would. And there's really no physical reason for distinguishing between a bilayer and a monolayer as long as it has these properties of having long hydrocarbons facing the inside, and on the outside, in archaeal lipids, as in all other lipids, are polar head groups, which can be a variety of things. By the way, the length of the hydrocarbon chains in the archaea is somewhere between 30 and 40 carbons. Now, at the end...
Is that longer or shorter than eukaryotic?
Well, depends. The usual bacterial or eukaryotic bilayers have lipids which have 16 to 18 carbons, so twice that much is 32 to 36. Here we go from 30 to 40 in the case of the archaea. So yeah, they're overlapping.
Okay.
In other words, the width of the membrane is not altered by this. Okay. On the other hand, they're tougher, and this goes together with the fact that the archaea are tough hombres. They are many of them are extremophiles. They beat the band for being able to grow at high temperatures, low pH, and so forth. So having a tough membrane is a good way of doing business. And this probably comes at some kind of a cost, but it's not a major cost because they are, after all, successful. So here we are with these interesting isoprenoids, right? And I bet you that when Michael lectures to medical and dental students, this comes up.
Not so much anymore. They don't really care. It's all about how they're examined, and it's no longer relevant. It's a biochemical curiosity.
Well, actually, in a way, they have a point, because as one of the oddities about archaea is that there are no known pathogens.
Right.
Even though they live in humans and in animals, there are no known pathogenic archaea, and that's one big question as to why that is. Right? So certainly have. Anyhow, we can discuss that some other time. Anyhow, so here are the archaea. So now to get into this paper, what they did is to look at marine sediments which go back a long way. They are off the coast of Peru. They go back 2.5 million years. 2.5 million years, am I right? I think that's right. Yes, 2.5 million years. So in terms of the billion of years we've been talking about, that's not much, but still it's a significant amount. And what they found is that the polar head group, in other words, the ends on the outside of these molecules, the ones that are sticking out both into the environment and into the cytoplasm of the cells, those can be quite different, and some of them have sugars, either 1 or 2 hexoses, and some of them have sugar phosphates. That is, the sugar is linked to the polyisoprenoid via a phosphate molecule. And these things are labile, and the whole point of the paper is to distinguish between the intact ones and the ones which are labile, because in time, in fact, they accumulate the lipids without these polar head groups. And this is where it's important, because the lipids with the polar head groups serve as an indication of living or recently living archaea, whereas the others, the ones without it, can be very old ones. And I gotta just tell you, the punchline of the paper is that if you don't include the old ones, and you don't realize that that are probably fossils, just measure the amount of these compounds in a sample, you arrive at the wrong conclusion that it's full of living archaea. So the point of the paper is to show that it's not all living, that it's in fact, a lot of it is from dead archaea, and you should be careful and kind of know what you're doing.
So take it with a grain of salt, more or less. From the ocean.
The lipids with the head groups you said are more recent, right? Like
they're labile. They're easier to destroy. They're destroyed more easily. So if you find them, they're not going to be very old.
So this is about 7,000 years. Is that the number I'm getting?
Yeah, that's a number.
Right.
That's one number, which is
And then the ones without the head group are really old. They can be millions of years.
They can be millions of years old. Maybe as much as 7 million years. Maybe longer. Maybe even older. So this is sort of an illustration of the games you can play by looking at fossil biomarkers. And I think this is a lot of fun. I mean, it's complicated stuff. You have to be very careful. All of this has to be taken, like you say, with a grain of salt. But it looks like it's very useful stuff.
So what would be a use for this? How would you use the presence of these lipids in various places to tell you anything? You can't date something based on this, but you could just say, well, here there were some archaea at some time.
That's right. That's exactly the point. It tells you there were some archaea that in a certain site that many million years ago, and that tells you something about the ecology, tells you possibly something about the kind of metabolism that was permissible. So, if you narrow it down to what kind of archaea, and I don't know how well you can do that,
right,
then you get even more information, more specific information. So the biomarkers are just a way of telling you who was there, and if you know other things about it, what they were doing.
Mm-hmm.
Remember, this all started with Elio doodling because he was listening to a story about the microbiome. And I think that's the real object lesson here, is understanding what markers to look for in order to understand events, because not everyone is going to have an opportunity to do whole sequencing. And the case made here is that DNA doesn't live forever, and forever means the age of the planet, 4.5 billion years. Right. And you have to look at sentinel events to try to give you a snapshot. And this becomes important for everything from global climate change to what we're watching emerge as a new discipline, and that's the microbiome. And remember, you all took me to task when we were talking on the last TWiM about microbes being able to make you eat certain things. And here the biomarkers are just but a tool in our whole list of being able to ask fundamental questions. Is this important? And I think that's what Vincent's getting at.
Right.
Yeah, I mean, we would like to give listeners an idea of why this means anything, right?
Yeah.
Mm-hmm. Especially, for the most part, it's clear when we talk about antibiotic resistance or microbiome, but here perhaps a little less so. But there's this whole area of biogeochemistry, which we touched on very lightly when we talked with Hazel Barton, the things that bacteria do in the caves. And this is
more importantly, the geologists who are looking for oil are actually using some of these microbial markers to tell them if there's literally the black gold in the location that they're drilling.
Yep.
Yeah.
It's important stuff. Yeah. All right. Thank you, Elio.
Surely.
That's that's illuminating for me, because I wasn't aware of these interesting fatty acids and how different they are.
Well, I'll tell you, the thing I didn't say is that how remarkable this is, that organic compounds can last billions of years.
I'm amazed at that.
It's so amazing.
And I would have thought a lipid of all things, but it's pretty hardy.
Why would they be so hardy? It's just, just amazing. I just thought the old world is all inorganic. Not so.
Mm-hmm. No, the membrane of these guys is quite interesting, and I've been looking at some sites while we were talking, and you can find quite a bit about the membranes of archaea and how different they are from other cells and so forth. It's quite interesting.
You want to put that in the show notes?
Yeah, there's a site at Berkeley, Morphology of the Archaea. They talk about 4 fundamental differences of the archaeal membrane compared to others. I'll put a link to that in the show notes. It's really neat. All right, let's move on to part 2 of TWiM 87. And as you heard earlier, Michael was at ICAAC this past week, where he was very busy doing ASM Live, and hopefully he'll summarize some of that for us. Did you get to see any sessions, Michael?
I did get to go see sessions. The organizers of ASM Live were kind enough to let me have the afternoons off. So I ran down to the posters, and to those of our listening audience that have never seen a general meeting or an ICAAC poster session, it's best to bring roller skates. But it's truly like roller derby, because you have to dodge in between all the people chatting about their science. And there's as many posters at ICAAC as there are at a general meeting, and the attendance is effectively equivalent, and
which is about how many? Give us an idea.
About 5,000 to 7,000 scientists. It was hard for me to judge because I got to the posters late after other people went off to either eat lunch or do other things. So I sort of was at the tail end of the posters. But the topics are, again, this is a meeting that is truly interdisciplinary. We have basic bench-level microbiologists like Vincent, Elio, and myself, as well as the clinical folks. These are practicing clinicians who take care of patients on a daily basis. So we have infectious disease physicians as well as pharmacists who take care of patients. And this was one of our first sessions was on antibiotic stewardship, which is an interdisciplinary activity between the microbiologist in the lab who's determining whether or not microbes are resistant to antibiotics, the physician who's prescribing the antibiotic to make the patient better, and the pharmacist who is really understands the pharmacodynamics of how the drugs work in the patients and how the microbes are becoming resistant to it. So it's really an interdisciplinary activity. And in fact, that's how we started ASM Live, as we started our first session.
Tell us what ASM Live really is.
It's basically the organizers of the meeting. This sort of morphed out of TWiM and TWiV, where Vincent and I, at one of the ICAAC about 3-4 years ago, had an ICAAC Live session, and we interviewed 3 of the top scientists who were presenting their findings. And it was so well received. We had standing room only at that meeting in Chicago, where we interviewed Arturo Casadevall, was one of the people I most remember, along with an individual from the United Kingdom who was talking about the ESBLs, whose name has just left.
So this is about the same format now?
Yes, it's designed like we do it. We talk a little bit about their science, and I guess the easiest way for our listeners to understand what we do is it's sort of like a chalk talk on the couch. I ask the investigators, what their science was about, and wherever their discussion takes me, I ask them questions like you do in a chalk talk.
The couch sounds a little bit Freudian, doesn't it?
It does, but it's easier for the camera people because you're sitting, so you're not bouncing around, and it makes for a little bit easier TV experience, and their microphones are firmly attached to them, so you get good sound. And you can go up on the internet. All of these sessions have been archived by the Crackerjack team from ASM. Chris Kandayan was the cameraman / director, and Ray Ortega, our normal sound engineer, was there on a camera. Along with, we had 4 cameras, and at some sessions the press came in, and we even had more cameras. Right. So it was quite something. And Nishant Prasad from New York Hospital of Queens and Frederick Reisman from Lund University. So like TWiV, we typically picked 2 papers that are similar to one another. And these 2 individuals started talking about antibiotic stewardship. And in the case of the hospital in Queens, they managed to actually save our tax dollars approximately $600,000 in annual costs just by properly prescribing antibiotics. Frederick Reisman from Lund told of how he stood up a program in Sweden And they really gave very compelling talks. I asked them simple questions. First, what is antibiotic stewardship? And for the most part, clinicians really want their patients to get better quickly. So they'll prescribe drugs based on what's actually running around the hospital. And oftentimes those drugs may not be the right antibiotic for whatever the patient has until they get the results back from the lab. So it's empiric prescribing, which for the most part works very well. So stewardship is actually using the right antibiotic for the right agent or right microbe at the right time and restricting drugs that are known to not have as great of effect in their hospital for whatever reason, whether it's they want to restrict it so the drug will remain useful longer, or it just doesn't work in that particular environment. And a lot of people, prescribing folks, bring their own personal biases with them when they begin prescribing, and the goal is to make their patients better. So that was the first session. And then we jumped in the next session to talking about a new single-dose influenza drug. As we're coming into cold and flu season, Rich Watley from UAB, who's a pediatric infectious disease specialist. So this is a pediatrician whose principal specialty is infectious diseases. He, along with one of the scientists from the company who developed this single-dose neuraminidase inhibitor. Neuraminidase inhibitors that you may be familiar with are oseltamivir, which is Tamiflu by its branded name, and you have to take these neuraminidase inhibitors within 48 hours of becoming ill, or 2 days of becoming ill, in order to see a lessening of severity of symptoms when you have frank influenza. And so this new drug, you only need to take one, and it's an injectable. So it's run in via IV, and it's got an advantage. You wouldn't think an IV-based medication would have an advantage over a pill, because most folks don't like to take injectable drugs because you have to be in the hospital or you have to run it in an infusion center. But this one is safe. It's effective. It's been tested, and it's licensed presently in Japan, and it's licensed in Europe, and currently it's before the FDA, and the FDA will rule on it later this year. So we may actually have it available for flu season this winter. But principally, the reporters who are also in the audience took both Dr. Whiteley, who ran a clinical trial at UAB, and Dr. Sheridan, who's one of the principal scientists from BioCris, took them to task about how many patients were in the phase 2 and phase clinical trials. Since the trials were initially conducted in Japan, does the drug work equivalently well in the population of the United States, where we have a more diverse ethnic background than Japan? And so you actually saw the open debate of science going on in this particular session. And the bottom line is the drug worked. And it was truly an interesting and provocative session. It went on for about an hour. So we talked about the trial and how to conduct a trial. And, that was pretty interesting for me to watch the reporters take the scientists to task, while at the same time letting the audience ask questions. One physician from UCLA came up, and afterwards he reported how this injectable is actually, they're already tinkering with it. They're thinking about pushing it via IV so you can actually administer it fairly quickly in the emergency room. I personally thought that this drug would have great utility in a long-term care facility like a nursing home,
right,
where one individual is exposed, and you can quickly line up people and infuse the drug, and you can protect them for a reasonable period of time if you have a suspected case of influenza.
There's been a lot of controversy over Behringer's. Is that the company that makes the not Behringer? Who am I thinking of? That makes Tamiflu.
That's Roche.
Roche, sorry, Behringer. Roche. They've come to task because they didn't release all of their clinical trial data, and it's not as effective as it was initially claimed to be. So, how did this look? Did this seem more effective when delivered intravenously?
Yes. And the other advantage to it is that some influenza, depending on the virus, has a GI symptom in which you vomit out the medication before it's been able to be absorbed by the system.
Yeah.
So right. This has the advantage over that. And the other neuraminidase inhibitor that is nebulized, zanamivir, I think is the trade name. If you have lung issues,
can't have that, right?
You can't have that, if you have chronic obstructive pulmonary disease or COPD, that drug is limited. So this adds another drug into our armamentarium. But the most important thing from a public health perspective is this material is stable at room temperature for 5 years.
Wow.
So no need to refrigerate it, and it's stable. So, in terms of thinking about stockpiling drugs for a pandemic, this is clearly one that's superior over the other medications, and its dry powder form is even more stable because you can then rehydrate it with the diluent that you would use to make up the meds. So that was pretty exciting.
Is it clear why it has to be injected? Does it not go through the stomach?
They've already looked at the oral delivery, and it didn't work as effectively. So they've been down that path, and they went to the injectable. They were looking at an intramuscular preparation, but it's too painful to do IM. So it was an exciting presentation. They had a bunch. There were like 20 posters on this particular topic at this meeting, and so this was one of the hot areas that people were looking at. The other new drug that we talked about is a new antifungal option. This is isovuconazole. And these two papers were presented by Kieran Marr from Johns Hopkins. She gave a very elegant summary synopsis, and Andrew Ullman from Julius Maximilian University. And they were talking about this drug in contrast to voriconazole for invasive mold disease in cancer patients, and this had far less side effects. And the voriconazole, as you probably know, Elio, has issues with dosing, in that the blood levels are different, and this drug has fewer side effects than the existing drug on the market. And so they presented in their posters, along with other folks, this new antifungal option. Initially, the audience was for immune compromise, and they called it cancer patients. And so I found that presentation. And again, the reporters who show up to this are typically for the clinical trial trade press, where they really know the art of doing exciting clinical trials. And it was really interesting watching them discuss these activities. And these were two investigators who were participating in the trial, and they were parsing the data, because here's the reporters have studied in detail the design of the trial. And it's for the beginning graduate student, dabbling, trying to figure out where their career path is, this really shows you alternatives to being the bench scientist, to looking at some of these different areas that you're thinking about. And then we also had, this was one of the sessions I just found absolutely fascinating. We had Laurent Porel from the University of Freiburg in Switzerland, and Kara Moret from the Oregon State Public Health Labs. And the folks in Switzerland have developed a new and fast test for looking for carbapenemase, the enzyme that degrades the last of the ultra effective beta-lactam drugs. And it's really clever. What they did is they pick a colony off a plate, and they're going to ask the question, does this colony have the gene to digest a beta-lactam drug? And so you put your substrate in, and it's a carbapenemase-based antibiotic, and you mix it up, and within a very short period of time, minutes to hours, depending upon your lysis protocol, you can quickly tell if the microbe has the enzyme to degrade the antibiotic. And they're developing it, and the detection is something from old-time religion microbiology. It's Congo red. Mm-hmm. And when the when the enzyme degrades the antibiotic, it lowers the pH. So Congo red goes from red to yellow, and even my colorblind eyes can tell red to yellow. And Karen Moray at Oregon State Public Health Lab has begun to tinker with this in surveillance to see how many of her isolates coming in from hospital labs have this particular gene. And as we know from our discussions of NDM in weeks past, the carbapenemase started out of overseas and has moved from the East Coast to the West Coast. And Oregon, of course, is all the way on our West Coast, and it fortunately doesn't have a lot of this. So this is very important for a public health lab. And Laurent Pourel was effectively saying, the importance in surveillance is being able to afford to do it. PCR is great. PCR is great, but, for the most part, it costs you about $40 an assay. Whereas this is literally accomplished for pennies in a test tube. So I found that discussion absolutely fascinating, and the audience did too. I should point out that there was a lot going on at ICAAC, and this was publicized in the Daily Planner. And so we had a standing room only audience every session, save for the last, which was a press conference on Ebola. So I was really pleased at the audience participation. The investigators were, of course, they didn't know what to expect when they sat on the couch. They came, and so I tried to make them at ease. I said, we're just going to have a conversation amongst colleagues. Just pretend that you're talking to your office mate and you're telling them why this is important and what you hope to learn, what you hope to gain. And I talked to them for about 5 minutes while they were putting on their microphones, and I said, ignore the cameras. And we just had a conversation, and it was a lot of fun for me because I learned a lot. I had to do a lot of homework too because I had to ask questions, but it was absolutely exciting. And then I got to do a busman's holiday on Monday. Charlie Gerba from the University of Arizona at Tucson came, and he talked about how quickly viruses can contaminate a building. And over this past weekend, Vincent's probably already discussed this on TWiM, but enterovirus D68 blew up over the weekend. And this is just a garden variety enterovirus, but unfortunately, if you have any lung issues in your preteen, it seems to adversely affect you and you need to be hospitalized. So Dr. Gerba's study was he used a bacteriophage, MS2, and he placed it on a doorknob of an office building, and he asked a simple question. How fast did this virus penetrate the building and colonize the workers? So within 2 to 4 hours, the virus was found on 40 to 60% of the workers and visitors in the facility.
Gee.
And he just deposited it on one doorknob.
Doorknobs are killers.
And what that really shows you is, first, when they handle the door, they don't completely sanitize it by using it once and you think, okay, I'm clear. I mean, because he only put the virus on one, and MS2 is a bacteriophage, so it's highly unlikely that I'm bringing MS2 from home. I mean, it had to be his MS2. And the fact that it was on 40-60% of the workers throughout the building within 2 to 4 hours. And I asked him what the hotspot was, and he says it's the coffee room. It's not the toilet. It's not the bathroom. It's the coffee room.
Not surprised.
And I guess the biggest anticipated session was on Ebola. And here we were very fortunate in that we had Lieutenant Commander Barbara Knust from the CDC. She's also a veterinarian, a DMV, and she's been on the ground in Africa investigating Ebola.
She looked tired.
Yeah, she's been running around. We had Gary Kobinger from the National Microbiology Lab from Winnipeg, Canada, and he's been on the ground running around in Africa as well as Canada, as well as one of the attending physicians, Anesh Mehta from Emory University, who actually took care of the very famous patients that were airlifted to the United States. And I think the thing I learned most is that you don't need negative pressure rooms to take care of these patients. You just need to control where their bodily fluids go. So you have to be very diligent in your personal protective equipment. And the biggest lesson learned from Dr. Mehta was the healthcare team is most at risk when taking their equipment off.
That's right.
That's often when they're most subject to contamination. So
yeah, that's what I've heard, that you have to learn the procedure for taking it off. There are a series of steps,
and they have to be followed religiously.
Yeah.
And the other thing with treating Ebola, and I think this is really important, as the Gates Foundation has gotten involved in, arguing to go to Africa, is I think the reason. There are a number of reasons why I think the patients survived at Emory's Hospital. First and foremost is likely they got the convalescent serum as well as the Z-Pak from the new experimental drug. And we don't know which drug actually worked, whether it was the convalescent serum or whether it was this product from the tobacco, because you only had 2 patients in the study, so you have no way of knowing. You don't have a control. You don't know what's going on. But I think what Dr. Mehta said is that they managed aggressively their electrolytes and their nutritions.
Yeah.
And I think that's actually what saved them, is the careful control of their electrolyte balance and the fact that they got enough protein. And they were feeding these folks by tube. And one of the patients in Atlanta, as we heard reported on the news, had profound diarrhea in excess of 4 liters a day. And, that's a really tough situation to manage. And so they were managing their electrolytes. I don't know which patient it was. They didn't disclose. But, I think that's the hallmark lesson from that.
I talked to Tom Solomon a couple of weeks ago, who is the director of a Global Health Institute in Liverpool. And that's exactly what he said. Electrolytes. IV drips is going to really make a big difference. And they don't do it religiously in Africa for many reasons. Right.
Yeah. And I think then a lady in their public session, I happened to be able to attend the public session because it was late in the afternoon. One of the laboratorians from another hospital that was going to receive a patient said, our lab workers are afraid to analyze samples. Now, so I didn't go up to the microphone to ask this question of the audience, so I'm going to put this out for the laboratorians who listen. The way I was always taught is you consider every clinical sample to be contaminated with the most serious viral diseases at the time you analyze blood. So if you're analyzing blood, of course, we think everything is HIV positive until proven otherwise. We think it has hepatitis B and hepatitis C until proven otherwise. And I learned from Dr. Barry Blumberg when I was a graduate student, and he was doing a sabbatical in the lab, and he, of course, developed the Hep B vaccine, at how stable this virus was. He jokingly said the safest thing you can do when you use a public restroom is bring some alcohol and set the toilet seat on fire before you sit down. But he was, of course, joking with us poor graduate students. And he was illustrating that this virus is very stable in the environment. And, today we screen lots and lots of blood samples in the developed world, and we do it routinely without serious incident. And so I think we can probably do CBCs and chem panels on these patients who are suspectedly having Ebola, as long as we follow the basic bloodborne pathogen guidelines all laboratories follow, and manage the samples appropriately. So, and Dr. Mentha answered the woman's question. He says at Emory, they have point-of-care testing in the rooms just to assuage the fears. But I think in a place where we're going to have the potential for treating a lot of patients, that may not always be possible. And we really need to investigate how to do the laboratory analysis in a safe manner, and to really get that information out to the laboratorians.
Wonderful. Sounds like you had a good
Nice.
time.
Sounds great.
And we only discussed some of them.
Of course.
There's more on. All of these have been archived by the great team at ASM, so you can go and watch them, and you can see how the scientists react to the questions. And all of the folks that I interviewed were as cool as cucumbers.
Wonderful.
On the couch.
Sure, it's because of you, Michael.
We tried.
Microbeworld.org/ASM live. You can find them there. We'll put a link in the show notes. We have a couple of emails here I'd like to read to you. First one is from Varun, who writes, "Greetings, TWiM profs. As a person constantly associated with clinical microbiology, I have seen the resistance grow up one by one. I couldn't agree more about the problem of using carbapenems owing to MBL. Michael?
I don't know what MBL is. He's taking
something beta-lactamases.
Owing to MBL. I don't know what that acronym is.
MBL. Yeah,
I always follow the rule of spelling it out the first time.
Well, I'm going to look it up. Metallo-beta-lactamase.
Yeah, that's what metallo-beta-lactamases. That makes sense. My brain is now functioning again.
In my personal experience, carbapenems have become almost of no use. In the last couple of months, I have also begun seeing resistance to some last resorts like tigecycline. A couple of days ago, I have also seen a clear case of colistin resistance. Tigecycline and colistin resistance is now well documented in the literature, hence I'm not surprised. Your thoughts? Clearly, we are desperately in need of new battle options. One of the papers that I happen to have read recently in connection is collateral sensitivity. I believe it is a TWiMable topic, at least a worthy discussion. And he sends a link to a paper in Science magazine called The Use of Collateral Sensitivity Networks to Design Drug Cycling Protocols That Avoid Resistance Development.
Well, that goes to the antibiotic stewardship issue as well. I think that's how stewardship is going to move to the next level, is with this collateral sensitivity type factored into their practice plans. And I think collateral sensitivity is an important topic to introduce to our TWiM audience. I don't think it will be too technical. I think it's right on point. This whole business of colistin, which is an old drug that's only been recently coming slowly back to the United States. It's been used in Europe for a while. And tigecycline, of course, was a new drug that was developed by our friend Steve Projam, who many of you in the audience know. Vincent, I know you've met him a few times.
Yeah.
And Steve was the guiding force behind the development of tigecycline.
So have a look at that paper, Michael. Maybe you want to do it in a future TWiM.
Yeah, I'll take a look at it.
Thanks for everything that you do. Twix fan. Dave writes, "Hi, y'all. Haven't flirted with 40 degrees Celsius recently, but the San Joaquin Valley real humidity is higher than theoretical due to decorative and crop tree respiration, I think, despite severe drought. Air quality the worst and better than it used to be. Ground level ozone cooks right up on still sunny days, not to mention particulates with a breeze. So much for pleasantries I previously skipped." I guess they have a drought there as well, right, Elio?
Oh, yeah.
The email writer on episode of August 14th called attention to scrubs in hospitals and cross-contamination. My limited experience leads me to think those thoughts delightful and heartily endorse it. Also, if a big place, imagine some of the hues. So this was a letter where the writer suggested different colors for different people in the hospital, of scrubs, that is. Mostly moved to propose hypothesis about the increase of scrubs worn promiscuously between hospital areas, but also in and out of the home. The lack of locker rooms and time were mentioned and deserve mention. Also, however, I believe many workers who are not surgeons have to buy and launder their own these days. The old binsful tend to walk off one by one, adding to facility cost. Why mess up street clothes then? I digress from my hypothesis. In the current social environment, a certain pride and glorious elevated status role in medical facility impels some of these garment decisions. I'm especially important, it hints, and busier than you. It extends easily to lab techs and nursing assistants. When observed in MDs specifically, however, it grabs the identity more simply than the longer white lab coat and becomes a source of silent pride. This is concomitant with decline of physician-surgeon's role as a social dignitary and repository of wisdom. Rather, dignity having been generally deflated, and thank God, in recent culture, physician-surgeons have become tradesmen. They are also finally no longer humiliated by mere lowly student status. They also really do have special skills and earnings to signify. They are thus deflated by their own identity search at base. They have abandoned role of interested, knowledgeable advisor and slipped into that of mechanic or technologist of uncertain trustworthiness. This sociological trend has been proceeding for several decades. Scrubs of identifiable hues, anyway, are a brilliant suggestion. So are locker rooms and time into the minute productivity demands to ceremonialize their use. They seem like a consciousness-raising device as well. Bottom line, the casual cross-contamination is reminiscent of 19th century practice. It deserves attention. Sorry, I shouldn't listen in the middle of the night and submit to urge to share by writing. All the best, Dave. It reminds me, here at Columbia, there's some older PIs who don't work in the laboratory, and they're in their offices in shirt and tie. And when they go to a seminar, they put on a white coat. Mm-hmm. But they don't do lab work. They just wear the coat to the seminar. So it's sort of what he's saying here. He says, I'm a doctor, I have a white coat on.
When I first started lecturing at MUSC 25 years ago, my senior colleagues who were working in the lab would put on their clean white coat to go lecture to the medical students.
That's fine, right? That makes a lot of sense, right?
As opposed to their dirty coat.
Yeah.
And I commended them for that. But when I lecture to the students, I typically don't wear a coat. I just go down there and leave my dirty lab coat in the lab.
That's right. John writes, Dear amphitropical podcasters, in TWiM 84, Melanie Thompson said she needed to come up with an allergy test for maggots before letting them eat people. Do the FDA and IRBs impose similar requirements in America? Does approval of maggots for use in America make it easier to get approval in other countries? And he attached a photograph of 3 Lucilia suricata, the fly licensed for use in the USA, eating a dead slug. Well, it turns out that maggot therapy is approved for use in the U.S. In January, the FDA granted permission to use humans maggots as a prescription-only medical device. I don't know if they did any allergy testing. It's approved elsewhere as well, so you can use it to clean dead tissue from wounds, basically, and other things as well. And let me read the last one from Michael. Is it funny that it's from Michael because it's to Michael? Thank you for all that you do. I love to listen to all your podcasts as I am at the bench. I'm a medical laboratory scientist, new terminology for medical biotechnologist. In TWiM 85, when Michael described the modified Hodge test near 53 minutes and 30 seconds, he made two mistakes. One, it was described that the lawn was of an E. coli that was resistant to carbapenems. That's not correct. It's actually sensitive to carbapenems, and we do a streak of QC organisms and clinical isolates from the carbapenem disc out to the edge of the plate. If the isolate has certain carbapenemases, it does diffuse, like Michael said, and allows the E. coli to grow closer to the disc. Two, Michael stated in essence that the modified Hodge test will detect metallo-beta-lactamases. There's our MBLs. That is not correct. It detects what is KPC?
Klebsiella pneumonia carbapenemase.
All right, KPC-type carbapenemases, well, and Enterobacteriaceae, but according to CLSI, the Clinical Laboratory Standards Institute, it is only 11% sensitive for the New Delhi metallo-beta-lactamase. I also attached a recent paper from JCM on a possible way to detect carbapenemases using liquid chromatography mass spec in about 75 minutes. Please keep up all the good work. I just finished my first master's course, heading towards a degree in biotechnology. I decided to continue on with school largely because of your podcasts. I started listening to TWiV in 2009, but only part-time because I believe there is a lot to learn in a clinical micro lab. Michael, MLSASCP. Well, thank you, Michael.
Thank you for fixing my mistake. I should tell the listening audience, when I prepare for a paper, I try to remember as much as possible and review, but I don't read scripts very well. If you watch the videos, you can see I have to go back and refer to notes if I'm scripted. And I try to do these podcasts as spontaneously as possible. And since I'm not a medical laboratory scientist by certification as you are, you're much better at me. And so thank you very much for capturing my errors.
Well, Michael, we don't pick them up either. So we depend on some of our listeners, and we're glad that they write in. We don't mind being corrected.
Oh, no. Fine. I'm the first to admit that I am not perfect.
All right, that'll do. That's a funny way to end that one, Michael.
Yeah.
TWiM 87. You can find TWiM at iTunes and also at microworld.org/TWiM. And do send us your questions and comments. You can send them to twim@twiv.tv. We do enjoy getting them and hearing what Michael said wrong.
Yes.
Not just Michael, everyone. We all say things wrong. I'd like to thank everyone for joining today. Elio Schaechter can be found at the wonderful blog Small Things Considered. Thank you, Elio.
My pleasure, of course.
Wonderful learning about ancient lipids today. Great. Really cool. Michael Schmidt is at the Medical University of South Carolina. Thank you, Michael.
Thank you.
And welcome back from ICAAC.
I'm going to recover this weekend.
Are you going off somewhere soon?
Nope, I'm done traveling for the month of September.
Yep. All right. I'm Vincent Racaniello. You can find me at virology.ws. I do want to thank the American Society for Microbiology for their support of TWiM and Chris Kandian and Ray Ortega for making it work. The music you hear on TWiM is composed and performed by Ronald Jenkins. You can find his work at ronaldjenkins.com. Thanks for listening, everyone. We'll see you next time on This Week in Microbiology. Cool.
Okay.
Ancient lipids.
Well, that was different, wasn't it?
How about that?
Both halves were different.
So, Elio, I heard a talk in Australia by this guy who gets very old jars in archaeological sites, and he finds fermented liquids in them. And then they do mass spec, and they figure out, what makes them up. Because apparently humans have fermented liquids for ages because they like getting drunk, I suppose.
Right.
And he tries to reproduce these ancient beverages.
Oh, I heard, yeah.
Have you heard of this guy?
I've heard of it, yeah. I don't know. I haven't tasted it.
And so there are a couple you can buy, and the story makes,
Having fun.
Yeah. I mean,
but you're talking about 4,000 years.
Not millions of years, yes. That's right.
It'll all be evaporated by then.
Yeah, it's not going to last that long. Anyway, it's pretty cool.
And 60-year-old Scotch is $700 a liter, and God knows how much 4,000-year-old Scotch would be.
Thanks, everybody.
Thanks, Vincent.
Okay.
Have a good afternoon.
You too. Bye.